Hey, welcome everybody. Today we're going to look at the nature of loaded fixed beams. These are things that can be found pretty much everywhere in nature, from bridges to skyscrapers to roller coasters. Really anywhere you can find a member or beam subject to loading that's fixed on both ends. So in a lot of cases, it's easy to forget why that system's inherent nature is the way it is. And in this particular case, we will look at why and how a railroad track deflects the way it does when being lifted. As you can see kind of here in this picture below, you can see the track being lifted a certain amount. How does that behave? So today, some goals are to guide your intuition. This is going to be a high flyby of key principles. And I will be concise, not protecting or withholding you from the truth. I'll give you everything you need to understand this system fully. And really, I'll try to minimize a lot of the exhaustive, mathy, rigorous details underlying everything. You just need a basic understanding of what a slope is, what's an area, or what's a force, or a torque, which is a force at a certain area, or what's a stress or amount of force per unit area inside a beam or material, and what's elasticity, which is basically how much a material stretches for a given amount of stress. So this kind of develops like a burning question that we need to resolve here today, and that is, what on earth does the deflection along a track look like? How does it behave? So in this picture here, we have the track at its initial state, and it's being lifted a certain way, and there's many possibilities of what it could be that we need to find. And on the top here, you can see the track being lifted, and you get to the end here, and you see a discontinuity or an instantaneous rate of change of slope. So it's at the slope, and then it instantaneously is horizontal, which would mean that there's an infinite moment at that point, which is improbable. It's impossible. So that can't be it. Another possibility maybe is the bottom light blue one here, and that one really doesn't make much sense either, because what force is causing the track to lower at this spot? I mean, it's being lifted, so there's really no force that will cause it to be lower. So intuition is telling me that it has to be probably somewhere in the middle, or something that looks like this middle color blue. So to look at this in detail and analyze it, we need to do one thing, and that is to mentally cut the track into many small segments. They say that the only way to eat an elephant is well, one bite at a time. So that's kind of what we're doing here, right? So we can look at the torque or moment and force at the start boundary right here, and then that gets translated to the next segment, which gets translated to the next segment, which gets translated to the next segment. And in doing that process, you can develop the entire nature of the whole section of track. So let's find out. The system's deterministic. That is, that there is one and only one solution that can occur given the initial conditions. They kind of say that the first step to finding a solution is believing there is one. And I believe that there is a solution out there that we're going to find. We need to strategically define parameters to discover all aspects of the solution. And we're going to use the derivation of material mechanics and repeated calculation from section cut to section cut to find the solution. So first, let's look at what we know. What do we know? So we can look at the geometry longitudinally across the track. So We know the position of the rear jacking force. We know the position of the front jacking force. We know the entire length of the track being lifted. We know the tie spacing, so these ties have some weight to them, and each one is going to pull the track down a certain amount at each point. We know the number of ties being lifted. We know the slope at the boundaries, and we know the height at the boundaries. And we can develop a small change in rail length between section cuts, depending on how many section cuts we want to make. So we know our section of track is subject to different loads. So what are those loads in particular? Well, we know that our sleeper weight plus our rail weight per unit length equals the entire track weight per unit length. And just for convention, I have the entire track weight pointing upwards, but the value is actually negative. And we know our jacking forces at the front and rear. So what do we not know? We don't know our reaction forces at the left and right boundaries, and we don't know our reaction moments at our left and right boundaries. So to find those, we need to look at a couple things, and that's for equilibrium. We know that the forces in the vertical direction have to equal 0. So our jacking forces are lifting the track up, our track weight is pushing it down, our shear force at the left boundary is pushing it up, and our shear force at the right boundary is pushing it down. So that develops this equation right here. And we know that our sum of the moments at any certain point has to equal 0. So I think of this like a wrench, like you're applying a force with a wrench, and then the bolt is applying a force the other direction. So similarly, we can look at the point at the left here. The jacking forces are going to rotate the entire track counterclockwise. Our track weight per unit length is going to rotate the entire track counterclockwise at the midpoint distance. And our moment at the left convention is rotating it clockwise, and our moment at the right boundary convention is rotating it counterclockwise. So, and then our shear force at the right side times the entire length of track is going to rotate it clockwise. And that develops this equation right here. So we have a problem, and that is we have more unknowns than equations. So we know it's overconstrained, making the system statically indeterminate. Pinned beams are much easier to define because you don't have these reaction moments at the boundaries. So just to move forward, let's just pretend and guess we know that the moments at the left and right boundaries.